Hey everyone, and welcome to this explainer. Today, we're going to step into the shoes of an engineering professor to tackle one of the absolute biggest global challenges we face. We're getting into the hard science of water pollution, but more importantly, we're going to look at the incredible engineering solutions we use to actually fix it. So grab a seat and let's just dive right in. Okay, imagine I'm standing at the front of a lecture hall, right? And I'm holding up two glasses of water. One is totally lifeless, murky, and brown. It's suffocating. It basically represents total neglect. But the other glass, it's a crystal clear, thriving stream, clean, alive, and ready to support a whole community. Well, the entire goal of civil and environmental engineering is to move us from that first glass to the second. We have to diagnose the illness, and then we engineer the cure. Here's our quick syllabus for today. We're going to start by diagnosing the damage, and then we'll open up the engineer's toolkit, looking at source control, recycling, and green infrastructure. Finally, we'll wrap up with governance and the ultimate challenge for future engineers. All right, Section 1, diagnosing the damage and looking at the ripple effects on our ecosystems. We really need to understand how pollution directly and honestly sometimes super subtly destroys aquatic life. The very first, most immediate effect of water pollution is an oxygen crisis. We call this eutrophication. Basically, when oxygen-demanding wastes enter a water body, it's an absolute feast for bacteria. Those bacteria multiply like crazy and consume the dissolved oxygen in the water. And the devastating result? Fish and other aquatic life literally suffocate. But it doesn't stop there. It's a chain reaction. When dissolved oxygen levels plummet, those surviving organisms become incredibly vulnerable to disease and toxic chemicals. So they're essentially drowning and being poisoned at the exact same time. To put some hard data to this, let's look at a pretty staggering number from a 2024 study on the Ganga River. They were looking at thermal discharge from a coal-fired power plant, and they found that near the discharge point, the chlorophyll content was reduced by a factor of 1.34. Now, why does that actually matter? Well, chlorophyll is how we measure phytoplankton, which is the literal foundation of the aquatic food chain. When you knock out the foundation, you create a state of hypoxia. The water simply cannot support life anymore. And that brings us to a specific, often overlooked mechanism of death in our waterways: thermal shock. This is a subtle but absolutely brutal form of pollution. Think about it. When a power plant opens up or shuts down for repairs, that sudden rush or sudden stop of hot water instantly kills organisms that are adapted to a very specific temperature range. Plus, basic chemistry tells us that as water heats up, its ability to hold on to dissolved oxygen drops. And the long-term effects of even tiny, gradual temperature shifts are massive. Take a look at this, just 2.7 degrees Celsius. A study in the Mediterranean Sea showed that a marine heat wave, where temperatures were just 2.7 degrees above the average, caused mass mortality across thousands of kilometers of coastline. We are talking about the total, devastating loss of corals, sponges, and algae. So as engineers, the big question is, how do we design facilities that don't turn our oceans and rivers into hot, lifeless bathtubs? Moving on to Section 2, source control and recycling. Let's open up the engineer's toolkit. Okay, let's shift gears from the damage we've done to the real optimism of the engineering solutions we actually have at our disposal. The absolute best solution? Stop the pollution before it even starts. That's the core of the pollution prevention principle. It means re-engineering our industrial processes so they just generate less waste right from the get-go. It means swapping out toxic materials for non-toxic ones and using better management practices on our farms to stop fertilizer runoff before it ever has a chance to reach a stream. It's the most effective and, believe it or not, often the cheapest approach. But what about the waste we do inevitably produce? While this requires a huge mindset shift for an engineer, waste is really just a misplaced resource. Take a look at the recovery rates for a new extraction flocculation hybrid system used in textile wastewater. We aren't just treating the water so we can dump it safely anymore. We are actively recovering 99.2% of the dyes, nearly 79% of the salts, and even 55% of the thermal energy, all to be reused in the very next dyeing cycle. That is the circular economy in action, right there. And the innovation doesn't stop there. EU-funded projects are developing advanced bioreactors right now that harness carbon, nitrogen, and sulfur cycles to create the precursors for bioplastics straight out of waste. Meanwhile, over at Temple University, engineers have developed a way to capture PFAS, those notorious forever chemicals, and microplastics using a completely chemical-free air bubble foam. These are cutting-edge, closed-loop technologies. They prove that with the right engineering, we can design systems where pollution simply doesn't exist as an end product.
This brings us to Section 3, Green Infrastructure Solutions and Working with Nature.
Let's look at how this builds into our physical environment, where civil engineering actually meets ecology. For a long time, we've been used to building with just concrete and steel, what we call gray infrastructure. But when you compare that to newer methods, it's night and day. Traditional curbside drains, they remove literally 0% of common pollutants. None. They just move dirty water from point A to point B as fast as humanly possible. Green infrastructure, on the other hand, acts like a giant sponge. It can remove up to 95% of common pollutants. By utilizing things like green roofs, rain gardens, and permeable pavements, we can build sponge cities that absorb, store, and naturally filter all our stormwater. And these nature-based solutions are incredibly effective when we engineer them as a sequence. Imagine what happens when runoff goes through a carefully designed series. First a green roof, then a bioretention basin, a swale, and finally a constructed wetland. Through that sequence, we see nearly a 99% removal of total suspended solids, over 95% of phosphorus, and 83% of nitrogen. The engineered vegetation traps the water in the landscape, promotes natural infiltration into the ground, and drastically cuts down the total volume of polluted runoff. It's just brilliant.
Want to see this in the real world? Let's take a look at the Wild Park Rainscape in Brighton over in the UK. This is a true engineering marvel. Step 1. Toxic road pollution from a busy highway is captured. Step 2. The water passes through vortex separators to pull out heavy debris. Step 3. It's naturally filtered through planted wetland basins. And the result? Step 4. 90% of the city's drinking water, which sits in a vulnerable groundwater aquifer, is protected from toxic runoff. It's basically the perfect marriage of structural and ecological engineering.
Moving on to Section 4, Governance and Research, or in other words, creating the right frameworks. Look, amazing technology alone just isn't enough. We need the right frameworks to back it all up. The most brilliantly engineered wetland or hybrid reactor is only going to be built if there's a system actually demanding it. We need water administration firmly managed by state or central governments with really strong, clear regulations. We need constant consultation with qualified experts, and we definitely need ongoing funding for applied research and public health engineering. Crucially, we have to mandate things like chemical mixture risk assessments, because stormwater isn't just one single chemical. It's a highly complex, dangerous cocktail. At the end of the day, strong policies are what create the demand for sustainable engineering.
And finally, Section 5, The Engineer's Challenge, Designing the Future. Let's summarize everything we've talked about in this explainer. On one side of the equation, we have the pathology, the illness we diagnosed earlier. Water pollution suffocates rivers, kills aquatic life via hypoxia and thermal shock, and severely threatens public health. But on the other side, we have our prescription, our engineering toolkit. We can prevent pollution right at the source. We can design closed-loop systems that recover and reuse resources, and we can build green infrastructure that works symbiotically with nature. The solutions are entirely within our reach.
I want you to really consider the gravity of this. We can continue to build with concrete, steel, and indifference, creating a world of dead rivers and contaminated aquifers. Or we can build a world where our infrastructure actually protects and restores our water. The technology is already there. The academic understanding is there. The only question that remains is whether we have the vision to actually execute it.
So I'm going to leave you with a bit of a homework assignment, as any good professor would. Look at your local water body. Could be a river, a pond, or honestly, even just a street storm drain. What is currently being done to manage it? Is it just old-school great infrastructure, or do you see nature-based solutions at play? And most importantly, how could you engineer it better? Take these concepts, look at your own environment, and start designing the future. Thanks so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.